Magdum sir. Magdum sir, please share the screen.
Hello, VV Magdum sir.
Yes.
Okay.
Yes, sir, you can
Patil sir,
start.
please start.
Okay. Thank you, sir. So, first of all, I welcome all the participants and today's our expert, Dr. Rajesh Lekkireddy, sir. First of all, I introduce our today's expert. So, today's session is on control system for EV drive train and protection. So, Dr. Rajesh Lekkireddy, sir, completed his PhD in electrical and computer science engineering from IIT Ahmedabad with research focused on advanced methodology for estimating series and shunt capacitances of 15 MVA power transformers. His doctoral work led to granted patents and multiple IEEE publications. During this period, he also proposed an advanced transformer protection algorithm to leading OEMs and the Gujarat State Electricity Utility. This work is currently under further development. In parallel with his research, he played a key role in establishing a dedicated special electrical machine laboratory where he implemented Simulink based speed control models and integrated real time hardware interfaces to enable hands on experimental learning. Also, in industry, Sir serves as a lead engineer at HCL Technologies, where he designed and validated Simulink and state flow based control algorithms for various clients, including Schneider Electric. His responsibilities, including control algorithm development in MATLAB simulation, MIL, SIL testing, and embedded code generation using Target Link and Embedded Coder. Dr. Lekkireddy sir specializes in bridging academic research and industrial practice in the area of power system, transformer diagnostics, motor control, and model-based design. His technical expertise includes MATLAB Simulink, State Flow, STM32 microcontroller, and its platform, embedded coder, and advanced verification and validation framework. So with this big biodata and experience in a particular area, now I uh, conclude the introduction of our today's expert here, and I request our today's expert to start the session, please. Thank you, sir.
Thank you, sir. Thank you for the kind introduction. Good evening, all. Thank you for joining the session, and I'll be sharing my screen. Is my screen visible?
Yes, sir, visible.
Okay. So today I'll discuss more on the live demo that was designed in the MATLAB. So quickly we'll go through each slide and we'll understand the theory behind the implementation. And we'll go into the MATLAB and we can, we can design, we can implement in the algorithm, we can implement algorithm in the MATLAB. Okay. So today's topic is basically control system for EV drivetrain and protection. So what I today I need to discuss, I would like to discuss is basically. So we'll start with the algorithm development to till deployment. How industries are following. What is the industry trend from starting from the algorithm development? How they will design, how they will verify, how they will validate, and they can deploy into the different MCUs. What are the best practices they are following, and what is the importance of those? So along with this, we'll see the live demo. So where we can understand easily how they are implementing. Basically, it doesn't look complicated, but we need to follow them to have a safe algorithm for the electric vehicle transition. So let's start the session. So basically, why EV is considered as a software-driven mission? Why control systems in the EV plays a key role for moving the vehicle from one place to other place. So why? Because earlier the vehicles are mainly mechanical driven. So nowadays the trend has changed. So everything electrification come into the picture for the mechanical vehicles, right? So so for moving a kilometer of EV, millions of loops are working inside the different MCUs, and each MCU is communicating with each other to move the vehicle, to drive the vehicle, and to get the torque, to pump, to escalate the current from motors, from inverter to motors, and how much torque is required, how much current has to be go through. So all these are internally communicating with each other, like motors, inverters, batteries, all are operating through the closed loop system. So this software will decide how efficient the vehicle has to perform and how safely the vehicle is going and what is the performance of the vehicle. So everyone knows the FOC control is widely used in EV traction system. So why FOC is very much useful, that we will see in the next slides. The next one is what are the expectations we can take it from the traction motor, so that everyone is known. So once if you think in a realistic way, so once we start the engine, once we start the EV, so we'll expect that it has to reach the maximum speed in very less time. So what does it mean in electrical terms? It has a high initial power and it has to move efficiently, and power density in the sense of the motor. So for the small size of motor, it has to give high power, and the torque ripple should be minimum. And what are the type of the magnet arrangement should be, whether it is a surface mounted or axial type. So what type of the arrangements to be kept in the motor. So depending upon this arrangements, also the mechanism of the motor has to be changed. Its characteristics basically will change, and what is the effect of the slot opening. So and similar performance related parameters. So then we'll move to the FOC. Everyone knows, I mean, this algorithm is known to everyone. So why FOC is very crucial, why it is important basically. So it will open up, it will enable the independent control of both flux producing and torque producing. It works similarly as a separately excited DC machine. So what makes the flux producing component that was adjusted by the direct axis current, and torque producing component is adjusted by the quadrature axis current. So basically we are converting the three phase currents to the two phase, which are rotating in the DQ frame. So this is a theory and this is well known to everyone. It has been using from past 20 years. So I don't want to focus more on the FOC. So we'll move. Sorry. So then why FOC is basically important is it gives a wide range of operation and high starting torque, fast dynamic response. It improves the overall efficiency. So if you think in a realistic terms again, so for a sports car, the torque should be high, torque should be high to quickly reach its maximum speed. If you go to the economy vehicle, the efficiency should be high. So all these requirements can be fulfilled by the algorithm. That is an FOC. But all these through so, based upon the ID values, how different types of motors we can utilize for the specific applications. If you take an induction motor, ID value is greater than 0, which will and IQ is common to everything. So for a surface mounted PMSM, basically the ID value is kept as 0. Why? Because its rotor is permanent magnet. We don't require to give additional current to establish a magnetic field. So there is no magnetic field is required. Field current is not required basically. If you go to the IEPMSM, the interior permanent magnet, so the poles are kept inside the rotor basically. So its ID value, if you keep negative, so we can operate it as an MTPA, maximum torque per ampere, at the low and medium range speeds, and the flux weakening operation. So flux weakening is above the base speed. Also, we can run the motor in a safe reason. So that is what it means. So these are the few parameters we can change within the FOC for different types of the motor. That is what this slide was representing. Then we'll come to the protection of EV drives. If you see the EV, it is a version, it is a system of both electrical, thermal, and mechanical conditions. So the continuous monitoring is required on all these devices to keep the vehicle safe and to operate in a precise reason. So what are the key parameters? What is the known parameters? We can keep it in, we can consider that as a fault current. and what is their impact? What basically it will happen if the value go behind the certain range, the maximum value, let us say. So if you take the overcurrent, then it will basically do the if winding will also get damaged, motor winding will also get damaged, and the inverter switches will get damaged. So it creates a overheating. That is the one thing. And over voltage, that the DC bus, the capacitor links, it may get damaged. So the overspeed. And a few terms are I don't go more elaborated. Why? Because this is a known theory. So the overcurrent, over voltage, overspeed, and temperature, sensor failures. If the sensor has been failed, so there is no feedback to the FOC. So it will lose the stability. So the entire vehicle will go to the unstable state. So that is what the open phase and low battery SOC, the state of charge of the battery. So this is what some of the key parameters I can say to have to take care. So this is an overall picture. So I would like to focus more on the protection logic. Why? Because the FOC controller is known. Known in the sense of the theory, how it will work, and the way where Clark Park transforms will come. And IDIQ will be coming from the feedback system. Then we'll give some reference values. Then there was the regulators, where regulators will convert VDVQ. And again, it was doing the inverse transformation to get VA, VB, VC. And those values will go to the inverter. And that was a loop. That is an entirely closed loop. So now I'll focus how protection logic will be implemented inside the MATLAB. There was a layer, you can just imagine there was a layer, FOC layer, where we'll get the currents as a feedback. Then what basically FOC controller will do, it will give the PWM pulses to the inverter. Then inverter will convert DC to AC, and that was going to the motors and the transmission wheel. This was the one layer. Above that layer, there should be a protection layer. For suppose, let us consider if some glitch has happened in the FOC and the current going beyond the limits. So at that specific point of time, what we need to do? So we need to implement certain algorithm. So to stop the vehicle, one thing in the sense of we will have to stop the motor or cut the power supply to the motor, or to cut the power supply to the motor, what we have to do inside, just be above the layer of the FOC. That is what we like to. I would like to demonstrate this protection logic. We can implement this logic either in the Simulink or in the state flow. Anyways, we can do. But why state flow is preferable for the protection, I will tell you. So basically, the user has given some input. He has requesting for the acceleration. So at that point of time, how much torque should be given to the motor? So how much current should go? So all these come as an input, and how much current was flowing through the inverter, that can be coming as a feedback to this supervisory controller. Then it will give some yes or no conditions to the FOC, yeah, this was in limits. So then you can start the control algorithm. Then it will start the algorithm. It will run through it. If let us consider if something has happened, and the protection logic will say no, you stop this, stop giving the PWM impulses to the motor. Then it will stop, and the entire system will come into the halt state. This is how it will work. So why state flow? Basically, we can, as I said, we can implement algorithm either in the Simulink or in the state flow. But why I was sketching on the state flow? The state flow can perform superior than the Simulink if the events are event driven. Event driven in the sense of, let us consider the vehicle in the halt state. And now I want to move, get into ready. So I have to give some input. If this was the condition satisfied, then the vehicle has to move to the ready mode. And after ready mode to running mode, then some conditions has to be satisfied. It was like an event driven. And when the hierarchical supervisory logic, let us consider parent model, and inside there is an subsystem. And what is the another importance of state flow is we can see it was in the form of states. We can visualize where was the trouble was, and let us consider if you have designed the algorithm for small parts, and after a few months it was the bulky. So we can visualize where the problem was. It is in a graphical representation. It has a different states. Within the states, there was a different conditions. There was an action. There was an event. So we can visualize all those things, and it is pretty easy if coming on the time sequenced operation. Like after 2 seconds, it has to be done, and wait for the 10 seconds. So all these conditions we can also implement the Simulink. When compared to the Simulink, the state flow logic is easier. So that is what this entire table is representing, and ISO 262 is a safety compliance that should be followed in the automotive industry. So that is also fulfilled with this state flow and simulating board. And one more important concept I need to share is the data dictionary. Data dictionary is simple. Let us consider if you're writing a C code. So at the initial lines, we can initialize the variables like int C, int ABC, float ABC, a kind of. We'll initialize the values. In similar fashion, in the entire model-based design, we'll create one dictionary where we can keep all the variables and we can assign the data types to it. So what is the why we need to assign? We can utilize randomly, right? In the simulation, we can do basically. Let us consider if you open the sim link, we can add the constant blocks or we can add the gain blocks and we can do some interconnection between all the blocks and we can name it. And why difficulty, where difficulty we will face basically. Let us consider you have one model and there are a lot of models which was created by your team members. So all models coming into one place and we are doing the integration between the different modules. Let us consider. So we have assigned, let us consider speed. I have assigned speed and the data type to its speed I assigned as int 8. Let us consider. If someone has assigned some, they have also designed for different applications, they assigned speed as int 16. Let us consider. Now the data type has been changed here. So what will happen if you're doing the integration? MATLAB internal software won't understand. Here there is an int 8, there is an int 16. There is a data type mismatches. So all these mismatches can be avoided if you create and centralized dictionary. So where we can utilize all those variables throughout the simulation and the state flow model. That is what it was saying, and it will give the easy collaboration between the motor, inverter, and protection, like their limiting values also. If you remember in the Simulink, there was an initial function. If you right click, there was one pop-up will come. There is an initial function where we can give the variables like x is equals to 20 or n is equals to 300, let us say. And that n variable we can use throughout the simulation. But the difficulty is in that block, we need to assign the data type. But in the initial function, there is no option to give the data type and what is their maximum minimum values and whether that is a fixed variable or constant variable and what is their sampling time. So all these can be arranged in a data dictionary and it is pretty easy. I'll tell you while we are going to the demo. That is too easy. And a few more, this is the guidelines everyone will follow in the industry. Why these guidelines are essential? I'll tell you one example. Let us consider in X company, some algorithm has been designed for, let us consider 2016, and they have designed some algorithm. Now at 2020, now the software has to be upgraded. So that software should be compatible for the all the MCUs, like boards, controller boards. Let us consider. So if there is an STM board, there is an Texas board. So I have designed everything in the STM32. Now they want to use in the Texas board. So this should work on both the devices by just changing its target board. Whether we can meet all those, so we can meet if we follow certain standards that was given by the Automotive Advisory Board. The few are the map guidelines. It is basically for the MATLAB simulation and the state flow. What map? Few things I'll tell you. What are those guidelines? So the naming conventions. Like if you drag constant from the library to the simulation file, that is considered as a constant. We won't give the constant. Why? If you keep the name as a constant and we generated the code, let for suppose in that entire thousands of lines, it will show constant everywhere, but no one can understand what that constant represents. In the simulation, we can do in the model, it is very easy to identify where the constant block was, what constant block was. But when that was converted into C code, there was a lot of functions, there was a lot of loops inside it. So we won't be able to understand when the C code was generated. If you want to compile it, if you want to find the bugs in the C code, we won't be able to understand what does constant mean. So that is what the difficulty was. So the naming conventions should be proper and all the connections should be proper. This we will follow. And there was a subsystems we'll keep, right? That subsystem hierarchy should not be greater than 5. Like inside subsystem, there is one more subsystem, one more subsystem. So those subsystems to be avoided and the maximum is 6. And one more guideline was mux and demux are not allowed. Basically, we'll use mux and demux in a regular purpose, but those are not allowed. In place of mux and debux, we can use bus selectors. Why this mux and bus selectors is, I'll tell you one quick example. If you keep mux 1 is to n, let us consider n is to 1. So while we generate that mux into the C code, it will give an array. So the array was like, let us consider 1 to n we are giving. So it will give 1, 2, 3, 4, 5, 6, 7, 8 as an output. Now, what is 1 represent, what is 2 represent, what was 3 representing? So that we won't able to understand while you're using mux and demux. But if you give the bus selector or bus creator, it will clearly give you that one representing some x1 like speed, and the second one is the torque, and third one is some current, fourth one is the voltage. That naming, it will give the structured variable. So that was the beauty with the mux. So the kind of some guidelines we should follow, and initialization should be proper. What about the Mishra guidelines? The initialization should be done at the starting of the code, and there should not be any dynamic memory, and like there is no data conversion. Like at some point of time, n is assigned with int 8, and other time we are assigning n as a int 16. That should be avoided. And the next one is, let us consider like kind of Mishra guidelines was there, and ASPICE, that is also one type of the standard could be followed in the automotive industry. So how can, let us consider, once we have designed everything, and we won't be able to check every step, right? It is not possible basically. Let us consider we designed everything and the entire algorithm is ready. Now we need to check all the guidelines. Is it possible to check all the guidelines? No, it is not possible basically. So for this one, to overcome this challenge, the MATLAB has its own application, like coverage report. And what it will basically do, it will scan the entire code or entire model, and it will tell us where was the mistake was, where this particular algorithm we have developed, particular line that was not meeting those guidelines. So based on that, we can make the changes and we can deploy it in the controllers, and it will go to the production. That is how this entire state will go. And now we will see, now we'll jump into the MATLAB without wasting our time. So there we will see how the algorithm has been developed, how it was tested, and what are the steps to be followed to get it tested. Once the testing is done, we can go with some report of what that report was saying to us, whether we have done all the type of test cases or we have missed something. A kind of we will do, and we will compare the results with the models and with the output which are coming from the auto generated C code. That also we will do, and later on we'll go how that could be go for the deployment. So all those will cover today, starting with the data dictionary and all state and the state flow. So I'll be closing this one, and I'll quickly jump to the models. Is my simulation file visible? Can someone please confirm?
Yes, sir. Visible, sir.
It is clearly visible, right? The state flow. Okay. Now this is a kind of
Yes, it is
protect.
visible.
Yeah, thank you. It is a kind of protection manager where I said in the user input there was a sensor and there is an FOC, and it was going through, right? There was a supervisory logic. That supervisory logic I tried to implement it. This is one of the ways. This is not the one particular way to implement in the MATLAB, but this is one of the ways we can implement. I have taken very simple example, like uh, what it was showing is, let us consider the vehicle was there, and now at the initial state to running state it was moving. During running time period, let us consider if the current has gone beyond the limit. At that particular time period, what how we should stop the vehicle, and we have to give some pop-up like it is a warning signal. The current is beyond this limit. This is the fault was occurred, that was displayed in the HDMI basically. So that was displayed, and it will go to the reset mode. So once the user has pressed the reset mode, then running vehicle will come to the halt state when that warning has come. So once that warning was done, then after some period of time, we'll give some particular time period. Then if the user has put reset button, then vehicle will go to the standby mode. Then the acceleration, then it was like a closed loop. So that algorithm I tried to implement it, that I'll share. And before that, I said data dictionary. So why data dictionary is important? First, we'll see the data dictionary, and then we'll move into this state flow and simulation, how I have done basically. So in the modeling, there was a few tabs, right? So there was a option called modeling. In the modeling, we can find out a lot of options here, like data dictionary, link to data dictionary, kind of. So try to open the model explorer. So in the model explorer, we have to go to the file here, then new, then data dictionary. If you click data dictionary, I will show you directly. This is how it will come. So it is trying to open new data dictionary. This is how it would be to create we have to give some name. Let us consider demo. Save. If you can see the demo, and it will give some options for us, like a design data. So similarly, I have given EVDD, that is electric vehicle DD, and there was a design data. So inside design data, I have created some variables. I can utilize those variables in the further algorithms developing in the state flow or simulation, wherever it is. So this is how design data will look like. It was very clear and nothing is there here, right? Now, if you go to the add tab, and there was an option called Simulink bus. So if you click Simulink bus, it will give some bus name. So we can rename it like application some in, let us consider. These are the inputs we are giving to the state flow. That's why I have given as application input. So don't give the name as an input. Why? Because input is already dedicated to the MATLAB internally, that variable input or INP. So if you create the names with that, it will give some random error. We won't be able to identify it basically. So give some unique variable names like application in, application out, or something, a kind of. So I have given an application in. So inside application, this is how that pop-up will appear. So there is an option here. If you see add, if you click, it will open some variable random one. So the first one is the name, the second one is the data type, the complexity, whether that is a real, imaginary, and the dimensions it will give, whether that was an array or a simple constant term. What is the minimum value, what is the maximum value, whether the dimension mode is fixed or variable, basically. In the sense of fixed is, the value is fixed throughout the running time. If it is a variable, that variable will change, that was given by the user as an input, that will change throughout the simulation. And if you go to the variable, there is certain complexity that will come in the MATLAB. We have to change certain settings to make it compatible to the state front simulation. And it will give sampling time. For each variable, it will give the sampling time. We can decide. If you keep -1, that is inheritance, that is, it will follow whatever the settings we have given in the model setting. It will follow the same simulation time. So similarly, I have designed a few variables. If you see, application in, inside application in, I have created 3 variables. One is the threshold to give the maximum values of all those variables, like maximum current, maximum voltage, maximum temperature, maximum speed. A kind of variables can be placed in the threshold bus. This is also a bus, like nested bus, kind of. So if you see the data type, I have given bus as a threshold. And this threshold variable inside the application in bus, and this threshold bus is a nested bus, and this threshold is here. So if I click threshold, again internally I have given variables like Imax, Vmax, temperature max, speed max, and all these data types are single. The complexity I kept as real, the dimension is 1, and the minimum maximum values here I have given. Imax is 0 to 100, Vmax is 0 to 400 volts, temperature is 90 max, speed max I have assigned as a 2000. All these are fixed. Now if I come back to the application in, then the second is sensor. So if you see the sensor bus is here. So if I click sensor, sensors in the sense of this is what the current we are getting as an feedback from the motor inverter end to the state flow or FOC or something. So the I motor, V motor, temperature and speed, all these are assigned. And the command, one more bus was there, and the CMD. In this command, I have given some enable signal. If the user has given, yeah, you go and start the vehicle. It's a command. Let us consider there was a touch board. We have a touch board in the car, right? So if you press start the vehicle, so if you click it, this enable signal will be activated. That is how it was given as a boolean. If that was touched and that signal become the true. If that was true, certain conditions will pass and there is a transition from halt to some engine start, a kind of. There is a reset button. If the user has given reset button, then it will go to the true. Then it will stop the vehicle and it will make the vehicle running to the halt state, a kind of. And the speed reference, ID reference I have given for the further applications. So if you see the app out and a few connections I have given, the control, fault and mode. So the control, what I kept inside the control is enable FOC. So if everything is fine and all the conditions have passed and there is no glitch, there is no maximum current violation, then the enable FOC will become true. And that enable FOC is directly connected to the PWM generator with some gain or multiplication factors. If this was true, like let us consider AND block. So there is an AND block. I'll give enable FOC to the unblock, and one more is coming out from the inverse path transformation. That there was a transformation. If this enable FOC is true, along with that values which are coming out of the transformation, then that will give us an output. If enable FOC was failed, let us consider due to some glitch, not in the glitch, due to some feedback errors, then it won't give as a one. So that and one will fail and there is no output. There is no PWM pulses and motor doesn't go to the running condition. That is how this was designed. And the torque limit is basically, it was also multiplication factor after that speed regulator. The speed PI was there. The reference speed will give. There was an PI controller. It will give the torque, and the torque can be converted into IQ basically. Then IQ is giving from the reference, and there was one more PI controller will come. Then there was an PQ. That is how it could be. So the torque limit is, we can consider that is a multiplication factor. If the torque limit is 1, so the entire maximum torque can be applied. If the torque limit is 0.5, then 50% of the torque is applied, a kind of. So based on that, I have given the torque limit here for the control purpose. And the next one is fault. If you go to the fault. So what are the different types of faults we can expect? Over current, over voltage, over temperature, then the sensor failure. So based on that, I have designed these four. And this fault state is an enum. So we need to design which type of, we need to name some fault state, whether that is a minimum fault, critical fault, failure. Some names we have to give to display in the driver HDMI. So that based on that, there is an enum. So if you go to the enum of the fault state, so if you see no fault, critical, minor, active fault, active derate, the kind some meaningful names I have given, I have assigned. This in the industry, what will happen? These are the same names that will be displayed in the HDMI. So there was some screen. So in the screen, if you observe, even in the mobile phone also, if you observe, there are a lot of options will come. So these many options they have given as an enum behind the that software. This is how that was named. So if you see the driver mode, I want to see where it was internally, which state was active right now, whether that is an initial state and standby state, running, derate, or false state, which state basically inside the software which it was running. So that can also be displayed. That is also possible. So for that also there is one more enum, whether that is in initial state, standby state. So to decide those, these are the variables has been assigned. So once everything is assigned, we need to give some apply here. Then we have to save this entire DD. So once it was done, is there any doubt still till here from anyone?
No,
If
sir.
I'm
No.
some quick mode, you can say me, I can slow it down. That is also done. Now, once the data dictionary has been done, so then the simple one, we have to go to here, link data dictionary. We need to click link data dictionary. So then we need to browse. So then I have created one demo file, right? This is how it look like. You just click and open. So I have given EVDD and the everything is default. So just browse and select that corresponding data dictionary files and just click apply and OK. Now everything is ready. Now we can use all those variables for our algorithm development or any development. So for that one, we need to, I have given data dictionary. Now I need to pass those inputs to certain block. Then we'll get some outputs like application out. Then we have to give those application out to something. So for that one, I just added input and this is an out basically. So this is how that input block look like. The simple one that is available in the Maths app. So just go to the signal attributes. There was a data type here. So you just click the data type, go down. So we have created a lot of buses in the data dictionary. And the data dictionary is right now linked with the simulation file. So it will show all those buses which are created in the data dictionary, like application in, out, CMD control, fault sensor, everything it will show. So what we need basically, the mother bus we need to give. What is the mother bus? There is an application in, inside application in, there was a lot more buses, right? That is an, I can say child buses, but we have to give the parent bus so that we can access anything inside that parent bus. So the application in, application out are the two parent buses. The application is in for the input, application out is for the output. That's it. So very simple. So the bus input I have given, just apply and OK. And here the sample time you can change, otherwise you can keep -1. So that will take the whatever the sample period it has a default. Now this is how it look like. You just type chart. So that is from the Stateflow library, and this entire will appear like this. So once it was done, then you give some input. You can connect this input to here like this, and this input we will go signal attributes, happy, apply, okay. The same thing is there. And similarly, if you want output, the same thing. You can give out there, and you can select application out here in the attributes like this, and you can just connect it to this chart, and our chart is ready. Now inside chart, so it was like a flow chart. You know, everyone know the flow chart, right? How the flow chart is, there is an input like start, then there is some condition, yes or no condition. If yes, we'll go this side. If no, we'll go this side. Then we'll come to the next condition. If yes, this was the condition. If no, this was the condition. If no, then there was sub conditions after that hierarchy, right? This is how we can implement this. Is simple like a flow chart. So I'll show you. There was a lot of options here in the state flow. You can go through the state flow. You can easily understand. That is very simple. So there was this first rectangle is a chart. We just drag and drop here. This is how it look like, and that is what this one. So this icon will say the default. Default in the sense of the first it will come to the state which one is considered as a default. So if you start this entire state flow, the first chart will be activated by this chart will be activated by why, because this is a default. So it is and the connections was similar to the MATLAB. We'll connect the constant to the gain. We'll just drag it, right? And similarly we can just drag it and drop it, and everything will be connected. So I have considered as I said in the presentation, I have considered these many states like initial state, ready, run, fault, and shutdown. In the shutdown, I have considered a few more, like a D rate. If the current is, there are two conditions I considered here basically. If the current is 100 amperes, we can consider that as a 100%, right? If it is just above the 100%, I can consider that as a fault, just fault, right? If it is going beyond the 150%, like 1.5 times of the current, then I will consider that as a critical fault. So this is how the fault can be segregated, critical or minimum fault, a kind of. So all those states I have added. If you see, this is an initial state. The naming can be anything. We can give some any names. Even I can give Rajesh as a state name. So you can give anything. So, but that should be has to give the proper name, which will reflect what was written inside the condition. That is how it is. And there is a standby mode, and there is a few more after the standby. So that is the running condition. After standby, where it has to come, the running condition or fault state or derate condition. So the three states were there. And for all the states, there was a transition. So everything should be given as a transition to go from one state to another state. We don't want to miss anything. Let us consider now it is in a derate state. Now it has to move to the initial condition. So for that one, we need to give some path to pass through it. If you see here, there was an input here, and this is the output. It will go here, then it will go here, and it will jump to the initial condition, a kind of. So this is how it look like in a high level. The first condition, there was a few conditions I have given. If that was satisfied, then it will come to this condition. If here there is an yes or no condition, if this is condition is satisfied, then it will go to here. If that was failed, let us consider it may go to here or here based on the which condition has been true. So that is how it was given. I'll share this file. It's okay. You can go through it. So the initial state in the state chart there is three conditions. For every chart there are three conditions. One is an entry, during, and exit. Exit might not be useful every time, but the entry and during conditions are useful. Entry in the sense of once it was entered, which variables has to be visible. That is what entry state. I just entered to the chart. These many variables has to be visible. The during is whenever the chart is active. Let us consider the chart is active for 60 seconds. For those 60 seconds, the during conditions will be executed every time. Like let us consider I have given sample time as 1 second. So now the chart is activated for the 60 seconds. For the 60 seconds, every 1 second that function has been called. Let us consider I have given function name as a speed during the during state for a chart. Let us consider here I have not given any during state. I will tell you this is just an entry state. Once it was entered, it will check which has been false and which is true, a kind. So now this the first state will say, now if you remember there is a drive mode I have given enum, which state it was, that will be shown in the display. So it will show drive mode dot in dot state. So in the drive mode enum there is an initial state. So that has been given. And this has to be displayed in the output. So I have given app out mode, which mode it was basically. In the mode variable, it will show as an initial state. Why? Because I have given that as an input. So then this is a function. It will show minor fault is false. Why? Because it is in initial state, there is no fault. So the critical fault is zero. I mean false, minor fault is false. There is no reset timer and the torque factor is maximum. Why? Because there is no fault. And I have given some initializations inside the function. So this is what the function is calling here. So if you go to here, so this is how all everything is false. Why? Because it is an initial state. So there is no overcurrent fault, over voltage fault, temperature. There is no speed fault. So everything is false. And even the enable FOC is also false. Why? Because it is at the initial state. Now I need to move it to the standby. Let us consider if the driving seat person has given enable signal. So the enable signal is true. If that was true, then the transition move into the standby state. So now it is moving to the standby. It will, and the mode will show it is in a standby mode. Now the same thing, entry conditions are same. And the during condition again check minor critical faults. So here it will check whether there was any fault. Why? Because now the engine has been stopped, but before that engine has been stopped, the vehicle has been run. So during that run time, it will check whether there was any fault. Why? Because we are not starting. If the vehicle has launched and we started, there is no meaning of checking these minor faults in the standby. Why? Because vehicle has not been started. Now let us consider I came from Bangalore to Hyderabad. Then in the Hyderabad, I halted the vehicle. Now at the second day, I started the vehicle. So I need to check before that there is any faults in the system. So to check, there is a function. So, and that function is this one. Here a lot more has been written and nothing. Here what I have written is if the motor current is just beyond the threshold, we can consider that as a minor fault. If it is greater than 1.5 times, then it is considered as a critical fault. They just if else statements and nothing more than that. For we consider four fault conditions, right? Four current, voltage, temperature, and speed. So four conditions for the minor fault and four conditions for the critical fault. And the last one is the update is if it is in a critical fault, which type of fault it is, whether it is critical, activity rate, and no fault. If it is a critical fault, that is what it will show. It will display as an output. For that one, this is else condition. Now it is in standby mode. Now we need to run it, run the motor. I have to give enable signal to the FOC. Yeah, now it run the vehicle. So for that one, few conditions should be satisfied. What are those conditions? Minor fault should be false. Critical fault is also false. Then enable signal should be true. So then it will go to the running state. And in the running state, it has to go through certain conditions. So now I have given the function as now enable the motor. Nothing is there. No fault is accessed. Now start the motor. So at the entry state, it will start the motor. Now during state, what will do? It will check. Yeah, for every call, it will check whether there was any fault. If that was a fault, now let us consider during running state, we found one fault. Let us consider minor fault. So once it will catch the minor fault, then it will come out of the chart and it will check for the conditions. Whether I have given any minor fault condition. If yes, then it will pass through the another chart. If you see here, this is the running state. I have given minor fault as true. So every time, see, this is the during, right? During time, it will check the function every time. Once it will found minor fault, then it will come out of this chart. Then it will go and check this condition. If this is true, then it will directly jump to the derate state. What derate state will do? It will reduce the torque. Basically, there was the maximum torque. Now it will reduce the torque to some 0.5. I've given 0.5 randomly. We can make it anything. We can make more complicated internal functions. We may also write, but here I have given randomly as 0.5. Now the torque limit has been reduced to the 50%. If the torque is reduced, then the current will come into the control state. Now, now it is in derate state. Now it will check whether the minor fault has been triggered off or not. If the minor fault has been triggered off, let us consider. If you see here, minor fault is false, critical fault is also false. If that condition is been satisfied, again it will come back to the here and it will run with the maximum task. This is how the chart. This is like an event base. If this was done, then go here. If that was failed, come here. If this was done, then again go to the another chart. The kind of loops we can trip off easily with the state flow. That is how we can play between the charts. And this is the fault state. If running condition is the critical fault is true, then it will go to the fault state and it will display this fault is critical. Once we found this fault as a critical, we'll give some time to reset that fault. If you find some fault in the inverter, if you see the inverter, there is a reset button will give everywhere in the grinder, mixie grinder also will give the reset button. If something has done, then entire will be get off. If you just press the reset button, then it will come into the enable state. This is how it will work, right? The similarly it works. So it will go to the reset timer, and reset timer I have given as a 5 seconds. For 5 seconds, it will wait and then it will come to the enable state. And that is what the function was given here. So here I have taken sample time is 0.1 seconds, that is 1 millisecond. So after 10 milliseconds, it will become 1 second. So that loop I have triggered here. So this function will be called 10 times. Then basically that was considered as a real time 1 second. But for that, 10 times is 10 times it was calling 0.1, 0.2, and then it will come to the 1 second realistically. So that loop will run every time. So here as given, if it is 10 times it is called, then that will be converted into 1 second. This is what it was. This is how it was. Basically, if we are giving some rather than 1 millisecond, 10 milliseconds, let us consider, then 100 times it has to run internally to get into 1 second. So that is how it was. Now this is how has been designed for the protection. Now we will see. Now you did everything. Now you need to test it. like internally we need to test it for the different test cases. First I'll give zero fault, then I have to check the output whether it is giving correctly or not. If I am giving just a more than 100 amperes, like 101 amperes I have given, so it has to show it is as a minor fault. If I have given voltage as 400 is the maximum, right? 1.5 times is max is 600. So if I go beyond 600, let us consider I have given 1000 volts. So then immediately in the next sampling time, it has to show it as a critical fault. So whether that was happening or not, we need to check for the different condition. That is how in the industry we will follow basically. We have to check everything. Let us consider if you miss something, that missing state is clearly visible in the coverage. That also I will show you. So once everything is done, let us now everything is clear. Now just right click and make the system as an atomic. So what is basically the atomic system or just a random system? So everyone know, right? In the MATLAB, we'll design something like some gain block, some FOC algorithm. Let us consider. So the FOC algorithm was created. How those blocks will be called and which priority? There was a lot of blocks we'll keep, right? As an integration. Let us consider I kept some 10 blocks. So on which priority the blocks will be implemented inside the MATLAB. So there was a hierarchy. It will go from left to right is a priority. The left one is the highest priority. The right one is the lowest priority. So it will go from left to right and from top to bottom. That is how the hierarchy will be run inside the MATLAB. So if I make the system as an atomic, so the entire 10 blocks can be considered as a one block. So there is no priority. Every block can be checked for every sample time. So there is no missing. I mean, there is no. mm, uh, there won't be any missing of the activating the blocks at certain sample period. For 0.1 second, all the blocks can be executed. Then the next cycle, again, all the blocks will be executed. This is how it will make if you make an atomic subsystem. So for make this, you just go to the block parameters. Just click this, treat as an atomic unit. Now you can make a sample time as 0.1. I made 0.1 basically. You can make anything. So once it was done, then right click. There was an option called test harness. So in the test harness, you just create. Why it was showing project manager? I have named this as a project manager. So test harness create. So there was an 3 parameters. So this name randomly it will give. So I am third time I was generating the harness. So it has given the name as FDP harness 3 or something else. And there is one click box was there. Make the harness externally. So I just checked that box. So that is why it was showing some path where I have to store this harness. Why we need to go to the external? Why? Because it will be useful while you are using for the other application. Then import output was there. Import we can make anything. I mean, we can generate the inputs from the workspace or from external file like Excel sheet, or we can make from the signal builder that was available in the MATLAB, a signal editor. Any from anywhere we can give inputs to this entire chart. Then we can check the outputs. So I have followed the test sequence. I will tell you what the test sequence is. It is an easier one compared to others. So just select the test sequence, then you go to the advanced properties and everything is, I haven't touched anything. If you see the verification mode, there is an option, software in loop testing and processor in loop testing. So for this, I just selected normal and click OK. So once that was done, it will show some bar here. So if you click, it will show external harness is ready for us. So I have already created the external harness. So that was showing harness 0901, right? So if I go to the file top level, if you see here, there is an harness, FTP harness 0901. This is just click the OK and that harness will come and that will be saved here. So if I open this harness, this is how it looked like. This the same whatever the chart we have implemented. Two side buses. One is the input side and another is the output side. So there is an from and to was there, right? So there was an app out here. I just removed that app out and I added terminator. Why? Because I don't want to pass this entire output to somewhere else. I just want to test it, whether that output is correct or not. So I added terminator. On the input side, the default, it will come as a test sequence. So this is how test sequence. And inside test sequence, now you can say me which values has to change basically. So this run this will come as a default. So these values won't come like 100, 400. Everything will come as an yeah, these values will come as a default. Why? Because in the data dictionary, I have assigned maximum values. If you remember, current is 100, voltage is 400. So now you can understand, if I make the data dictionary as a centralized one, I can utilize same variables and its values everywhere throughout the cycle. Either it is in development state or testing state or coverage state, everywhere those variables will applicable as a default. I don't want to change everywhere in the simulation throughout the simulation. So that is the beauty of the data dictionary. So everything will come as a default. Now here I can change whatever the values I want if I want to check the test cases. So now at the run state, I kept everything same, like I enable signal is false, everything I reset false. So everything is false, 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 and nothing has been changed. Now I have to make the transition after 0.1 seconds while running. If the 0.7, 0.1 second sample time has been crossed, then this transition will check for the next step. It will have given step 1. So then it will come to the step 1. If you see here in the step 1, the values has been changed. If you see the I motor, the sensor current I make as a 50. Here it is 100, right? Randomly I made 50. And this 250. And I haven't changed everything. I haven't changed anything. Everything is in certain values. It is below the maximum value. I just made enable signal as true. Why I made enable signal as true? It has to come from the initial state to standby mode. If you remember in the chart, enable signal is true. Then initial to the standby mode, it has to come. So I made it as a true. Then after 0.1 second, it will check for the step 2. Then it will go to the step 2. In the step 2, if you see here, the current I have given greater than the maximum value. So if this was found by the algorithm, what could be the expected output? Expected output is a minimum fault. Some fault I have given. I couldn't recall now. Minor fault, right? So this is what expected. So if that was done, it will give some warning like a minor fault has been activated. So after 1 second, then it will go to the step 3. In the step 3, I made it as a 400 and 50 and enable signal is true. Okay. This is not required. I will make 400 as 600, let us say. So if I make as a 600, again it is more than 400. So here also expected as a minor fault. Now let us consider minor fault was done. Then I will keep everything within the limits. What does it mean? From the minor fault to the running state, it has to go back from the delayed state to the running state. So expected is running. Then after this, it will go here and it will check what are the values I have been given. So I have given V bus as 1000. So basically there is a 400. It is more than 2 times. So if it is more than 2 times, it has to give as a critical fault. So the expected is critical fault. So after 5 seconds, why I kept 5 seconds? If you remember here, the reset time is default as a 5 seconds. If I keep 5 seconds, it will wait for the 5 seconds at the fault block. Then after 5 seconds, the condition is satisfied. Then it will has to go to the standby mode and it has to stay at the standby mode. So that is what it was doing. After 5 seconds, then it will go to the enable signal as false. Then it will go to the standby mode. Then enable signal is false. Then it will go to the initial state. This is how the hierarchy should be done. So we'll check whether that is happening or not. So I'll keep side by side. I'll minimize it. If you remember each block, this is an initial state. I'm just giving the glimpse. Standby, running, fault, derate. If the minor fault, it has to be there. If it is a critical fault, then it has to come to the fault state. Then otherwise it has to be running state. This is how that entire algorithm should be 1. Now we will check. This is not a harness one. Yeah, this is a harness. See, now I'll run step by step. I'll go to the simulation. Okay, this is a run coverage. Rename it. As of now, I'll off the coverage. Then I'll go to simulation. Now I kept maximum as 10 seconds. Now I'll run it. If you see, if I press run, it will come to here. Now it is at the run state. Now you see there is no sample time. If I click, so 0.1 seconds. So 0.1 second is satisfied. That means it is true. So once it is true, it will go to the step 1 and check all these variables. If you see here, initially it is an initial state. Now it came to the standby mode. Why? Because that enable signal is satisfied. So that was satisfied. It was coming to the standby state. Now if I click, now this is also satisfied condition. Now see here, this is also satisfied. It came to the step 2. In the step 2, I have given the motor current is 0. So if you see here, so it should be minor fault. It has been identified. The next cycle, it come to the chart at 0.2 seconds. Then it will check whether there is any fault or not. If there is a fault, the next step it will go to some other chart. That should be expected one, right? It has to go to the derate state. Why? Because the current is just beyond the maximum value. So if you see here, now it was checking the condition. Yes, this condition is satisfied. If the condition is satisfied, then it will move to the derate state. Then the torque has been reduced to the 50%. Now if I click something, then again it will check. If the minor fault, second state it will check. So it will be there at the derate state. Why? Because I kept as a 1 second. It will wait for the 1 second, then it will go to the next step. So now it is operating at the derate state. Now 0.3 to 1.3, that is 1 second. Now again it is moving back to the running state. Now it is at here. Now the expected is it should be at the running state for another 1 second. Now it is coming to the fault state. Why? Because here it is given the current voltage is 1000. So it should be the critical fault. See, now it is in fault state. If you see the variables internally, if you see the reset timer here, it is 0, right? Now I'll quickly run it. It will stay here for 5 seconds. Now see, reset timer is 1. Now initially it is 2.3, now it's 3.3. So it is 10 milliseconds. Right? So it is become 1 second. So reset timer is 1. At 4.3 it will become 2. Then 3, 4, 5 a kind of similarly quickly. 4, 5. See, it went quickly to here. Why? Because this condition is satisfied. It went to the standby mode. In the test sequence, I have given 5 seconds. After 5 seconds, the enable signal should be false. So this was satisfied. It went to the initial state. So now we will visually we can understand this is how it was working. But we need some proofs, right? We need some proof to show some other team members, for our reference. It has been worked, right? So to check that one, there was a data inspector in the MATLAB that will come in the here in the state chart. So if you click the data inspector, we need to log the signals. This is what I did here. If you remember, if you see here, I logged signals on the output side and the input side. So once that was done, this is how it looked like. I mean, these are the 4 blocks I subdivided. We can check it from here. The different patterns we can select. So if you look at the left pan side, so if you click protection manager, so this is an output basically. These 3 are the output. This test sequence is an input, right? So this is what the sequence is. I mean, this is an input and this is an output. We can check quickly. So first I'll check the threshold values. I'll make I max. So I've given as an, so sorry, this is max sensor, right? Sensor value, I motor. This is how I changed. Initially I kept 50. After I make it as an 150, then after 1 second, again I made it as 50 amperes. So, right, this is an input I've given. Now here we'll check the VBus. So VBus, this is how we changed. Initially we kept as a 300, then 400, some 200 I kept. So then I made it as a 1000. If you remember, the 1000 I made after 2 seconds. So now here we will check what is the fault state. See, initially no fault. Then it went to the active derate. Why it went to the derate? Why? Because the current is greater than 100 amperes. So immediately it went to the derate. Then after that, after some conditions, the derate it is came back to the no fault state. Why? Because the torque has been reduced. The current came to the down reduced state. So there is no fault. Now it is running. Now after 2 seconds, what we did basically, we have given some input as 1000 volts. So then immediately it went to the critical state, and it was there at the critical state for the entire time period, if you observe. And here we can see the mode, which mode it was basically. Initially in initial state, then standby, then running. The current was maximum. Beyond maximum, it went to the derate state. Again, the current has been down, so it came to the running state. Then the voltage is maximum, then it went to the fault state. It was there for the fault state after certain time period, then it came to the standby mode after the reset. If you count from 2.3 to some 7.3, there is a 5 seconds time period. The 5 seconds it came to the standby mode, then again it went to the initial state in the next sample period. That is how it was saying. So this will show the proof that yes, our algorithm is working fine. So this is just one test case I have tested. We can make the 1000 test cases. We have to check everything for different. This was the voltage, this was the current, if these are the combinations, what was the. So all the conditions should be satisfied. This is how in industry we will check the test cases. This is what called as a mill testing, model in loop testing. I designed the model. I was testing that model. So that been considered as a model in loop testing by using the test harness. So this is the one thing I need to share. And another is, let us consider now our model is working fine. Now I need to make the model into, I need to generate the C code from the model. Yes, I generated. But while converting this model to the auto-generated C, there might be some glitches. It is not like that every time that should be proper. If my model is working fine, we won't be able to say for 100% sure that that entire code should work. That is not the possible case. That code may get failed. So there was certain conditions like fixed point tools. There are some points was there that may get mismatched. So then the output, whichever we are getting in the model, that might not match with the C code output. There is a condition. Yes, we can. That was true. So how we can check it? How we can check our model is entirely correct? If there was a glitch in the C code, then we have to come back to the model and we have to make the changes. And again, we have to do the model in loop testing. Then we have to generate the C code. Then the C code outputs has to be matched with the model in loop testing. So this is entirely a cyclic process basically. But manually, it is not possible to check everything, right? So let us consider, see, this is a very simple example. There is a more than 10 charts was there for the comparison. So every time manually, it is not possible to check whether the charts are matching or not. Every time, that is not possible, right? So to overcome that challenge, what is the way we can do in the Max app? Yes, there is a way called as a simulation test manager. What it will do, it will reduce that burden. It will do everything, and it will give what is the difference of the charts and where the difference is and what is the tolerance. If there is a difference, how much difference it was, 100%, 10%, 1%, everything detailed it will give visually. So how we can do that one? So there is a go to application. There is an I'll finish this. Don't worry, in 5 minutes. Go to the Simulink test. I'll save and close. See, So I already made a Simulink test. I'll just open it directly. If we click the Simulink test there, this is how it will get open. So just go to the test. There is an option called new, then test file from the model. Just the select which model you need to do. So we did this one, right? 0901. You just select that one, just open. And here the test type you can select as the equivalence. Why equivalence? We are comparing model in loop, software in loop for the equality test. So I selected equivalence and the path you just add, create. So it is already open. So yeah, I'll directly go. This is how it will come. Just go beyond it. And this is model we are checking. So if you click this model, these many options will come. If you clearly see, there is an option called simulation 1 and simulation 2. Simulation 1 for the model in loop testing. Simulation 2 for the software in loop testing. So what are the changes we need to do? The very simple change. So go here and check the harness. With default, it will come. Here, just change this simulation mode to normal. Normal is model in loop. If you want to do the software in loop, then you select software in loop. So for simulation 1, I did this one. If you go to the simulation 2, then in the settings, I made software in loop. But unfortunately, the software in loop file won't run in my PC. Why? Because there is no compiler for the to execute mex wrappers. That the compiler is missing in my PC. It won't run. Even if I run it, it will throw error. So I you do the necessary changes if you have a compiler and just save and run the file. If you run, then see this is what failed was. I'll just show it will if there is no compiler, it will throw error. And what it will do internally for the equivalence, the model in loop will be tested 2 times and it will compare those model in loops again. The result will always come, there is no difference, right? The same thing has been compared. That is what it did basically. See here, and the equivalence criteria it has shown. If I drag, see here, output 1 is normal, output 2 is normal. It is comparing normal 2 times. It will give the difference as 0, of course, right? So the equivalence, if I go to the equivalence, I just click one thing, any one random variable. See, this is what was enable FOC. So what it will do, basically how it will work, test manager, if I have an compiler. So it will match those graphs and it will tell what is the difference and how much tolerance to. So it will reduce our manual burden. It will make it automatic, everything. See, if you want anything, you can compare everything. It is a task limit. So this is how we can do in the Simulink test manager. If we want a report, let us consider. So then go to the test. This is a test sequence report. It will generate basically, but we can avoid it right now. And one more thing I just want to cover quickly is the test harness. Just 2 minutes is required for that. So what I said, right? We need to follow certain standards like MAB, Mishra, ASPICE. So how can we check? We won't be able to check manually, right? It has to give something. So this is what you have missed. This is what it was done. So this is where you haven't covered the test cases. So some automatic tool has to give us to say this is what missed. So for that one, just go to the apps and this is a coverage analyzer. There's an option. Just click it and this coverage will come here. The coverage is off here, so just on it. Now simply you just run the analyzer. Now if you see here, this is how the report is. It has a lot of pages. So this is how it will. Derate state has been executed 9 times. Fault state is executed 51 times internally. So this is how it was. Yeah, there are some few red lines. Why those red lines? I'll tell you. It will show. If you see here, so this temperature max, we haven't checked it. If you remember in the test cases, we have checked only for the 2 cases. One is for the current and voltage. We missed the temperature and speed is right. So we haven't checked. We haven't touched it. The test case is failure. So it will show this is a failure. That is how this red one is saying. So it never came to the true. This test case you have missed. That is what it was saying to me. Even for the speed remote, this is true is failed. So that is what it will show. It has a lot of pages. So this entire will say coverage basically will say this is what you missed. This test case you have been missed. So you can do the test cases to pass this. This coverage should be 100%. This coverage should be everything should be 100%. Otherwise, it something has been missed. This is what basically it will do. So I quickly close it. And this is what I just want to share the live demo for a particular algorithm development. This is how we will do. So the quickly what I did is basically we need to develop model with the data dictionary. So once the model is ready, we need to write the test cases by creating the test harness. So we need to cover all the test cases. Once the test cases has been finished, we have to check the outputs. If you feel the proper output was there, then you go to the Simulink test manager. You check the model in loop output and software in loop output and compare. Is there any difference or not? If there is no difference, then go and check the coverage to check you whether you have missed anything. So once that everything is looks fine, then you come to the modeling simulation, then you can generate the C code. That is known, right? So if you come here, there is an, it won't come basically here. Otherwise, give the generate C code, that will come, pop up. Why it is not coming? Why? Because the harness is open here. Once the harness is open, it will get locked basically. Now see, everything has been open. Now, and that's it. This is what I just want to say. If you have any doubts, please you can ask me. I already generated code and view code. It is not there, it's okay. And this is what I want to do. The thank you for the session. If you have any doubts, please ask me.
Participant, any doubt regarding this session? Please unmute the mic and ask the question. Dear participant, any doubt regarding this session? Please unmute the mic and
Yeah, I'll stop sharing and
Hello, sir.
yeah, ma'am.
How will you understand that we have invoked the automotive standards in MATLAB?
Yeah, actually, if you are trying to generate the C code basically by using embedded coder has a default. It has to follow all these MAB Mishra guidelines. So once you started generating the C code, it will throw error if you are doing something wrong. If you are not meeting the standards, you are missing something. If there is a data type conversion is missing, so then it will definitely throw the error while we are converting this model to the C code. Actually, I am trying to do that one, but it is not loading basically. I'll try. I'll share again.
Sir, then C code support for automotives is separate, different because it has to incorporate the automotive standards.
Yes. That is different. Embedded coder is basically dedicated to the MATLAB, but most of the time industries will follow the target link. There is one more. It is similar to the target link. So there are few more. Embedded coder is dedicated to the MATLAB, and similarly, the target link is for the DSpace. So a kind of different apps was available for generating the C code. So those C codes are all, even embedded coder is also guided with the map, not for the Mishran map, the map it will follow. But for the A Spice, there is an dedicated apps was available with the industry.
Dedicated app. Can you name it, sir, please?
Application like embedded coder. Embedded coder is a part as an application as a part of the MATLAB, right? MathWork. MathWork was released with that embedded coder. Similarly,
Correct.
the DSpace has been the target thing. So similarly, one more, there are a lot more tools are available to make the model. So similarly, everything can be integrated with the MATLAB. MATLAB is like a universal, we can integrate everything. Even DSpace is also integrated with the MATLAB. So similarly, so for ASPICE standards, the people will use for different application, different like target link embedded coder, they will use different application.
Okay,
That can
sir.
also be
Thank you, sir.
integrated with the MATLAB. Yeah, thank you.
Sir, just what I would just like to tell you is that this is a very big, complex problem about which you have shown very nicely everything. I think the modeling in MATLAB, how many of us have been used? I don't know, but simple development of simple model using some simple state flow study that if you could throw the light on that in MATLAB, then I think it will be very helpful for going further ahead for the participants.
Yeah, actually, the time is very limited, so I just quickly tried to cover all those. Yeah,
Yeah,
I'll
yeah,
definitely
sir. Yours is very
if I get
best,
it.
no doubt. Excellent it is.
Thank you, ma'am.
Thank you,
If I
sir.
get a time, I'll
Thank you.
definitely do. Yeah.
Sir, at least you can give us some files where we have some simple set of problems and the state models and the actual flow, how to build
Yeah,
it
ma'am.
in
I'll
MATLAB
definitely
model.
share. I'll share a few links. You can go through those links. There is a lot of examples are available in the Maths app. In the Maths work
Okay,
also,
sir.
there is lot many examples are available for the state flow and like FOC, integrating FOC with the state flow. So if you go
Uh-huh.
through those files, then definitely you can understand.
Okay, sir.
I'll
Okay,
definitely
okay.
share. Even I'll share this whatever the algorithm I just sampled it. Right? I'll share that file also.
Uh, okay, sir. Thank you. Thank you.
Thank you, ma'am.
Any question?
Actually, I would like to say one more thing is that this is how, I mean, the problem is simple, but there is a lot more cycles we have to go through to make a one product which is come to the production state. So this is what lengthy process we will do in the industry to make it happen. So if you can practice it, it is definitely helpful for everyone.
Sir, could you tell us some direction to the research in modeling
Uh,
in terms of EV, sir? Mm.
Um, I'll share, ma'am, after this session. I'll definitely share with the emails. I think Praveen sir can populate it. I'll share it
Okay, sir.
with yeah,
Okay,
a
sir.
few problems also I'll share. Yeah. There is a lot more scope in the drives basically. We'll think FOC has been there for 20 years, but still the people are facing with the algorithms. A lot more troubles was there. Even for the MATLAB, simple supervisory logic, which I have shared, there also there is a lot more trouble right now industry is facing basically.
Uh-huh. Okay, sir.
But I'll share, yeah.
Okay, thank you.
Okay, Deepal sir.
Hello, sir.
Uh,
Uh, th- Thank you
shall I end the session?
for giving me opportunity.
Okay,
If
please
anyone
continue. Please continue.
having any question, then I will wait for few minutes. Is there any question from participant? Okay, thank you. So first of all, thanks for giving me opportunity for vote of thanks. Thank you, sir. I would like to express our sincere gratitude to Mr. Rajesh Lekkireddy, sir, for delivering session on control system for EV drive train and protection. Obviously, your expertise and your session will helpful for us, and I hope all the participants will use this particular knowledge for their research work. Those who are researching in the modeling of the EV sessions and the control system. Also, I would like to thank our HOD sir and organizing committee for arranging this valuable FDP session and all the participants for their active engagement. So after this, next session will start at 7:30 p.m. So with this segment, I conclude this particular session will over. Thank you, sir.
Thank you, sir. Thank you for joining us.
Thank you, sir. Thank you.
Thank you. Thank you, sir.